All right, so this is section 9.2. This one's a hypothesis test comparing two population proportions, which we set up in 9.1. Here's an example. It says the following example are based on a study from UNICEF, and UNICEF's an organization that basically studies, it's part of the UN, United Nations, and I think they study children's health issues. It says from a random sample of 825 school-age girls all over the world, 693 are allowed to attend school. In a random sample of 861 school-age boys from all over the world, 750 were allowed to attend school. And it says to test the claim at 2% significance that the proportion of girls worldwide who are allowed to attend school is lower than the proportion for boys. Okay. So we have this whole issue of getting our data values. And so I just want to remind you from up above, this is the statistic we're computing for two proportions. So you're going to need sample sizes and sample proportions from each population. So just let's get back down here and say you'll need to gather p hat 1, which is x1 over n1, and p hat 2, x2 over n2. And you have to check, you know, I mean, you can get n1, n2, you'll need an alpha, which is the level of significance. And you'll need to also check, now just for a moment, I'll be erasing this, but we used to say NP at least 10 and NQ at least 10, okay? But P and Q are two population proportions, and nobody surveys whole populations, so you're not going to know P and Q. So we'd put a hat on these and say N times P hat. Now, just real quick, N times P hat is N, and remember P hat is going to be like X over N. So the N's cancel. This is just X. So N times P hat is actually the number of successes. So you can do N times P hat, but they usually just tell you how many successes there are. There needs to be at least 10. And then N times Q hat is the number of failures. So let's just erase all of this because it's a little too complicated, more complicated than it needs to be. So how about we say check N times P hat, which is the number of successes, is greater than or equal to 10. And N times Q hat, which is the number of failures, that also needs to be greater than or equal to 10. Okay, any questions about that? And of course, we got a problem to do here. So P hat 1, this will be for the girls. It's 693. There are 825 girls altogether. And these are just girls sampled from all over the world. Randomly, I got this, this is simulated based on an UNICEF study that I did several years ago. Okay, so 693 divided by 825, and let's keep three significant figures. Oh, except for it's exactly 0.84. Okay, any questions? And then we'll get our p hat 2 here. So that's with the boys. There was 750 boys going to school out of 861 of them. Okay. That's 87%. I'll say 0.87 1. So that is a little higher proportion for boys going to school. But again, this is not an entire population. These are samples, and samples include error. And so you have to take these numbers with a grain of salt. They are from samples, so it's not necessarily proof yet. Okay, I see a question from Bren. Are they supposed to be greater than or equal to 10? Yes, that is the case. It's the n greater than 30 that we use when working with means, but this is a different rule. With proportions, we do the greater than or equal to 10, always. Okay, let's go ahead and line some of the stuff up. N1 was 825, as you can see. N2 was 861. I guess we can do our alpha. It was 2% significance, it says 0.02. Okay, and then our check. Let's do girls first, and then boys. For the successes, you don't have to compute it because it's given. There were 693 girls that were going to school. Okay, and of course that's greater than or equal to 10. Okay, any questions? It's hard to read. Don't like it when it happens like that. 693. Greater than or equal to 10. For the girls, the fails, you're going to have to subtract. So there were 825 girls minus the 693 that get to go to school. So that's 132 girls that don't get to go to school. But that also needs to be at least 10. And these are our criteria that allow us to use the normal curve. And we have to use boys next. So for the boys, the successes are the kids that go to school. So for the boys, it was 750. And of course, that's greater than or equal to 10. And then the fails are, for the boys altogether, were 861 boys minus 750 that go to school. Okay, so that should be a 111, which is also greater than or equal to 10. So everything's good here. I'll just kind of bracket it and put a big check mark here. I have checked, as proven by the check mark. Okay, any questions? Now, the null hypothesis is always the same, and that is that we're claiming that there's no difference between the groups. That'll always be the case. So your null hypothesis will be that the population proportions are the same for girls and for boys. So let's put that down. Same proportion. And maybe that's not true, but we always assume they're equal and then try and prove otherwise. Okay, any questions? Okay, and then the alternative hypothesis is going to be one of the three, right? So you're going to do less than, greater than, or not equal. And what do you think here? It says the proportion of girls worldwide who are allowed to attend school is lower than the proportion for boys. Any questions? Lower. So they're saying that for the girls, the proportion is lower than the proportion of boys who get to go to school. Okay, so that's a lower proportion for the girls. Okay, any questions? Okay, so that's easy enough. The test statistic is the thing we worked out in the previous lesson. So I'm just going to kind of slide back a page or two. And here's our Z statistic that will need to be doctored. So this is not the final version of it. So I don't know. I think mostly don't write the denominator yet. Okay, and again, that's our TS, test statistic. It's just a Z-score of the difference between the sample proportions. Okay, so let me help you out with the things we're going to fill in here. First of all, the null hypothesis is always assumed to be true. The null hypothesis says that P1 is equal to P2, but it doesn't say what these values are. It does say they're equal. If they're equal, then what's the difference between them? Good. So we will always put a 0 for the difference between P1 and P2. So that's the mean. The mean difference is the difference of the means. If we're assuming the means are equal, then the difference will always be 0. And the null hypothesis never changes for this test. The alternative hypothesis just changes from less than, greater than, or not equal. Okay, now again, to reemphasize, the null hypothesis tells us what P1 and P2, that they are equal, but it doesn't tell us what they are. And that's a problem for the denominator. I don't know what I'm going to put in down here for P1 and Q1. Q1 is 1 minus P1. I know that. What's P1? It doesn't, the null hypothesis makes no statement about the value. It just says they're equal. Right? Same thing with P2. I don't know its value. All right, so whenever we don't know some population measurement, remember P1 is a population proportion, then we always turn to our samples to estimate the value. Okay, so you don't know the population proportion, why not use the sample proportion? Now don't write this either, because I'm going to change it. It's not going to work either. Why not use the sample proportion? P hat 1 and Q hat 1 would be 1 minus P hat 1. Same thing with the other sample, P hat 2 and Q hat 2. So that's a step closer. We're using sample data to estimate the population data so that we can get our standard error in the denominator, which is great, except there's one problem. P hat 1 is not going to be equal to P hat 2, okay? And which is fine, but technically you're supposed to be using the same value for those two. The null hypothesis says that the two population proportions are equal, and we always assume that's true. I should be using the same value for P1 and P2, whatever it is, because the null hypothesis says they're equal. P hat 1 and P hat 2 are not equal. So what we're going to do is, again, these are just proportions of kids that are allowed to go to school. All right, so why not, if the girls and boys are supposedly going to school in equal proportions, why not mix the girls and boys together and get one proportion that represents both groups? So just real quick, let's add one note here. I'm going to call this P bar, and it's just going to be the total number of kids all together that are getting to go to school, divided by the total number of kids in the two samples combined. Okay, this is called the pooled proportion. pooling is where you put groups together, okay? We put the boys and the girls together here to make a pooled proportion. Okay, that now represents the boys and girls, which are supposed to have the same proportion going to school. Also mentioned Q bar will be 1 minus P bar. If you didn't think, you would have guessed that probably. Okay, so, and then up above, I'm supposed to be using the same proportions here. So I'm not going to use P1, Q1, P2, Q2. Those are supposed to be the same. So we'll just represent them as P bar and Q bar for both. So that's a little headache. I'm going to get rid of this comment. It is not useful anymore. Okay, so it looks bad. You do have to compute this new proportion, P bar. So let's do this on the other side of this here. I guess we have to do P bar first. So P bar, x1 plus x2 over n1 plus n2. Okay, so total number of boys, total number of girls. For the boys, there were, for the girls, there were 693 going to school, and for the boys, there were 750 going to school. Okay. And then when we divide by the two sample sizes, again, we're pooling them. Total number of girls was 825. And the total number of boys was 861. Okay, so here we get it, one proportion that represents both groups, which are supposed to have the same proportion attending school. And this is an estimate of that common proportion. My calculator gives a fraction for the answer. So in case I just remind you how to handle that if you don't remember. So if you entered this as I did, using the fraction button, looks great, but I don't know what 481 divided by 562 is. And so there's an approximate equal button above the enter key. And if you hit that, it says it's 0.85587. We'll go 0.856, which is pretty close. Okay, and then you'll need that Q bar. So 0.144. Okay, any questions about all that? And I'm going to try and get some space back here. Okay, and so we have to compute this test statistic. So this is a little bit of a pain. So I'm just going to copy the formula here and then evaluate it. Maybe a little smaller. Okay, so here goes nothing. P hat 1, just gonna have to keep going back and forth here. So P hat 1 was 8.840 and the other one's 0.871. So those are the two P hats. And then the difference between P1 and P2, while we don't know their value is, what the values are, hypothetically, we assume that there's no difference. So the difference is 0. And then the standard error down below, I'll put the square root in a sec, I think. So I have P bar, write really small if I can. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay, and then this is one of the harder computations we've had to do. So I'm going to show this on my calculator real quick so you can follow along if that helps. And let me focus it real quick. Oh, of course, I don't know the numbers. This is always the hard part here. So is that blurry? I can see all the dirt on my calculator, so that's a good thing. Okay, so fraction, and I'm going to be kind of going back and forth here. So it's 840871. Got it. On top. Okay, 0.84 minus 0.871 over square root. Oh, that did not. Nope, square root with a fraction inside. Okay. So the numerator of those fractions is 8568 times 144. Over n1, which I think is 825. Okay. Now don't leave the square root. So your blinking cursor, once you leave that fraction, the blinking cursor still needs to be under the square root symbol. So make sure, and then plus another fraction with the same numerator. Okay. And now your calculator starts scrolling and you can't see the whole expression. That's fine. And what was it? 800 and something. 861. Okay. So can't see it, but it's going to be so precise because I did it all in one shot. So I'll say negative 1.81, I think. Okay. So is that statistically significant? Negative 1.81. It's almost 2 standard deviations apart between the boys and the girls, but it's not quite 2 standard deviations. Okay, any questions? So you got to be able to get that z-score. It's kind of ugly. Of course, I ignore that 0 in the numerator and the parentheses. Going on. Now the critical value. All right, so it's the bottom row. Z-scores are in the bottom row of table A2, so let's get that real quick. Table A2 is easy enough. All right. There's no degrees of freedom for Z distribution. So for the degrees of freedom, you just go to the bottom row where it says large. That's large different degrees of freedom, but at the same time, these are Z-scores. Okay. Our alpha, I think, was 0.02, and this is a one-tail test. Okay, so take a look at that. 0.02, one tail. Bottom row of the table where the z-scores are. See if we can get that real quick. One tail, 0.02. So that's a lot of standard errors for statistical significance. So I get a 2.054. You guys agree with that? Again, it's 0.02 one tail. It's a one tail test. This was a left tail test. Okay. Oops. Right, so what was it? 2.054? I've already forgotten. Sad. 2.054, I guess I didn't. Okay, and then what I wanted to do real quick was on the alternative hypothesis here, let's make sure we know that that's a left tail test. Less than points to the left. It is the alternative hypothesis that determines the tail on your test. So less than, left tail. Greater than, right tail. This one's left tail. And technically, negative 2.054 standard errors is significant. That's our critical value. Okay, and our test statistic was negative 1.81, which is not in the tail this time. It's close. I don't ever like. I always want to give them a break when it's close. But anyway, that's our test statistic. And I'll just make a note here. It's not significant. Okay, so from these data, the girls did go to school in a lower proportion, but it wasn't statistically significant, and therefore you can't say anything about the whole population of girls. Not from these data. I think there's lots of data out there that talk about the disadvantages of girls who want to go to school, depending on the country they're from. But remember, this looks at the whole world. So. Okay, any questions? So we have to do a p-value next, which is table A1. This again is the z distribution. The t distribution is table A3. Normal distribution is table A1. Everything is z on this test if you look through all the computations. We have a z up here, a z critical value there, and now a p-value from the z distribution. Let's draw a little bell curve here. No, they're not very good. And our test statistic is a little bit to the right of the critical value. This was a negative, what was the test at? Negative 1.81 here. And that's the test stat. Okay. And then the area of that tail is the p-value. Okay, but this is a normal distribution, so this is table A1. Okay. So our z-score, you want to do negative 1.8 in the first column, and then 0.01 in the first row. And that's how table A1 works. There's no degrees of freedom here with the z distribution. Okay, any questions? Okay, let's just look that up real quick. Doesn't look like I've opened that today, so let me grab it. So we say negative 2.51, no, negative 1.81, right? I'll have to verify. Negative 1.801 is this guy right there. But I still call this significant, but it wasn't statistically significant, not at a 0.02 alpha. 0.0351. I'm hoping it was negative 1.81. Yep. That's your p-value, 0.0351. Okay, so remember, we said if it's less than 5%, it's statistically significant. So this is significant. But not enough. At alpha equal 0.02. So technically, alpha is deciding how small the probability needs to be significant, and that's why we call it the level of significance. Okay. Any questions? Okay, so I'm going to grab that little thing I was writing before. So be patient with me while I copy. Oops, no, darn it. So I wanted to copy this thing again. It's just a rephrasing of the paragraph right above it. So I'll just put it here again. It's just this paragraph that's above. But anyway, our p-value is 0.0351. Now this is bigger than our alpha. Greater than 0.02, which is alpha. Okay, and so that means that we're in this second case, we don't reject the null hypothesis, so we don't support the alternative. So I like to write fail to reject. So fail to reject the null hypothesis, which said that the proportions are equal. That does not mean we support it. You can't support something that you haven't proven. We do not know that the population proportions are equal. We just failed to disprove it. And we don't want to act like we know something after this. So fail to reject the null hypothesis, and that means don't support the alternative. H1, which had said that P1 is less than P2. So these data do not support that claim. So let's go ahead and make that comment. These data do not support the claim. I'm going to go ahead and add an alpha equal 0.02. That girls go to school in lower proportions. Than boys worldwide. The difference was significant, but not as significant enough. So I want to put that down here because it kind of overlooks an important point here. The difference was significant. With p-value of 0.0351, but not enough. At 2% significance. Okay, so it could be, you know, I think we're saying there is a significant difference between girls and boys, but it's not as significant as what was asked for this test. Highly significant. Now I see a question from Susan who says, I confused myself about the 5% you mentioned when comparing the p-value and alpha. Oh, yeah. Okay, so let me, would I mind refreshing? Yeah. Okay, so then what I was referring to, I'm gonna have to go back to the previous lesson. So I think I put notes down at the end of 8.4. So let's see if I'm right about that. Don't see it? Oh. No, yeah, I think it'd be the end of 8.2 then. Hoping. No! Ah, this was a comment that we did in 8.2. See, we don't want to come up with this black and white answer. The problem is to say that something's either significant or not. If that's all you're allowed to say, then you're going to be making harsh judgments sometimes, and you're neglecting those cases where it was close. So we said anytime the p-value is less than 1%, 0.01, that's highly significant. But if it's between 0.01 and 0.05, it's still significant. It's not highly significant. And that's the situation we're in right now, Susan, where the p-value is 0.035, okay? And we're saying, you know, with a 2% level of significance, technically that's not significant enough for this test, but it was still 0.035. And so you don't want to overlook the fact that this is a significant difference between girls and boys. It's just not significant according to the rules of this game, which was 2%. How's that, Susan? So just remember, alpha is the level of significance. That's the rule of significance. That's the rule of the game for one test. But that does not affect how you should look at p-values. This is just sort of a rule of thumb at how I look at p-values. The smaller it is, the more significant. We should not think in terms of black and white. Significance is a sliding scale, okay? I think we can all agree that if the p-value is bigger than 10%, this is something that's going to happen randomly all the time. So that's not going to be significant. Okay? But when things have a less than 1% chance and then they happen, we go, ooh, that's significant. And then there's this whole range in between significant or highly significant and not significant, where we want to allow a little elbow room so we're not making black and white statements. Okay, because life just isn't like that. Continue. Hypothesis tests sort of sound black and white, and I think it's better that you have a more sophisticated view, and that's why I'm showing this table here. Okay, and maybe I'll, just for those who will appreciate the reminder, I think I'll go ahead and copy that into our lesson so you can see it again if you're looking at the notes online. Where would I put it though? Okay, now the next thing I'm struggling with, just one sec here. Is the time. So it's 11:04. And I think what I want to do is I'm going to hopscotch a little bit because let me look at Canvas real quick at the schedule. I think we're behind by a lesson, so let me just double check. Where's Canvas? Here we go. Okay, so it says today's the 8th, and we're supposed to get 9.3 done. So we've done one hypothesis test for 9.2. So what I'm gonna do is, I'd like to get caught up, because honestly, I don't wanna get crammed in the last week of class. I wanna take I wanna take that last week of the semester, which is, coming up. And I'd like to completely use that day to review for the final, which is to say that let's do a problem in 9.3. I still want to be able to say I've done it, and then we'll fill in when we have time. Okay, so 9.2, we've got one example in. The next one is left blank for now, but it's identical to the first one. Okay, so we're going to do, I think, try to do one example from 9.3 because we've already laid the groundwork for this. This is comparing two means. So let me see if I can go back to my iPad here. Pardon me while I try and figure out what's going on with the iPad. It's frozen. Okay, let me stop that share. I'm going to start a new one here. There we go. Please work. There we go. Okay, so we've got another example in section 9.2. Let's go ahead and read this. It says researchers wanted to compare the proportion of females who are left-handed to the proportion of males who are left-handed. The researchers randomly selected 815 females and 575 males. They observed that 66 of the females and 60 of the males were left-handed. We will test the claim that the proportion of females who are left-handed is lower than the proportion of males who are left-handed. We will test the claim at the 5% significance level. Okay, so null hypothesis is going to have something to do with P1 and P2. The alternative clearly says that the proportion is lower for females, so we'll say P1 is less than P2, where the females are going to be, the female proportion is P1 because they are mentioned first. Okay, now the null hypothesis should always say these are equal. Now, before we begin the test, maybe we should do our gathering of data here. So we're going to have to do a p hat 1, which is going to be x1 over n1. So these are the females. There were 66 females who were left-handed out of 815. And 66 divided by 815 is 0.810. Okay. P hat 2 is x2 over n2. And there were 60, these are the males, 60 males that are left-handed out of 575 males. And let's see, that's 0.104. And as always with proportions, we're carrying 3 significant figures. Okay. Obviously, the N1 is 815. The N2 is 575. At some point, we have to do P bar and a check. We're here, so let's do P bar. That's x1 plus x2 over n1 plus n2. So it's the same numerators, but you're combining them, and the same denominators. Okay, like that. Maybe I'll make a little space here. Okay, so when you do that, the P bar comes out to be 0.0906. And that makes it clear that I've made a mistake on P hat 1. Okay, so that should have been 0.0810. Sorry about that mistake. Okay, now we have to do our little check. So let's check. We have to do successes and fails for both males and females. So for the females, successes was 66, which is big enough, greater than or equal to 10. And then the fails, out of 815, subtract the successes, and that's 749 fails for the females. Those are the right-handed, or not left-handed anyway, so that's greater than or equal to 10. We're good. Now the males, so successes, it says there were 60 left-handed men, so that's greater than or equal to 10. And then the fails are the right-handed, I guess, men. So that's how many males? 575 minus the 60, which better be 515. And that's greater than or equal to 10. So we got our successes and our fails for the females and the males. Our check is done. We're good to go. All right, so once you have that, I guess we're clear to do our test statistic. And we worked this one out previously in section 9.1 with a modification. Okay, so there's the formula. And let's go ahead and put our numbers in. Remember, the difference between the population proportions is 0 because we're assuming they're equal. So assume the difference is 0. And P hat 1 was 0.081 minus P hat 2, that's 0.104. And then, of course, we're subtracting 0, so we just ignore that. And here comes the messy part. P bar is 0.0906. And Q bar is 1 minus P bar. That comes out to 0.9094. Over N1, which is 815. Okay, and then the next one has the same numerator, 0.0906 times 0.9094 over that sample size, which was 575. And I wrote really small, and it still didn't fit. Just a bummer. So I'm going to shrink it, if I can manage it. bad. Okay, so we run the numbers on that. And that should come out to be negative 1.47. Okay, that's your test statistic. We'll use that to find a p-value. But before we do, we have to do a critical value. So for the critical value, you want to go to table A2. Okay, so remember, for degrees of freedom, when it's z, you just go to the bottom row where it says large down there. Okay, our alpha is 0.05, and it's a one-tailed test. Okay, like this. Okay, and when you look that up, looks like it's going to give you a 1.645. Okay, and this is a left-tail test because H1 points to the left here. Makes it a left-tail test. So I think I'll move this guy over here. Okay. So that's the definition of statistical significance. Anything less than negative 1.645, that's our critical value. Okay. Now, it's worth remembering that our p-value, let me see if we can line this up real quick here. Okay, so our p-value is negative 1.47, which will be to the right of negative 1.645. So again, this is z. Test statistic negative 1.47. Okay, and the area to the left of that is the p-value. Like that. And so for our p-value, should use table A1. Okay, and so just as a reminder how that one works, it's a p-value table essentially. And you look up your z-score on this table. Nearest 10th in the first column, so you go to negative 1.4 and then out to 0.07. So when you look that up, you should see 0.0708, which is the area of the left. This is a left tail test, so this is perfect. The p-value is 0.0708, like that. And that's a lot bigger than alpha. So the p-value is 0.0708, which is bigger than I think alpha was 0.05, yeah? Which means we reject the null hypothesis. Sorry, we fail to reject when it's larger. And don't support the alternative. HA, I think it said that there's a female proportion that's less than the male proportion, so P1 is less than P2. We have no evidence for this. So the data, even though it was a smaller proportion, it's not significant, so it could be just random. the data do not support the claim that a smaller proportion of females are left-handed, than males.